Okay, interval notation. What we're trying to do here is describe intervals of of the real numbers, and the simplest ones are intervals. And here's one. Um, here's a picture on the number line, and for this one, what we're trying to do is describe the set of points that are between 5 and 10. We do want 10 to be in the set, but we do not want 5 to be in the set. That's not there. So here's a better description as an inequality that with the numbers, it's the numbers h that are strictly bigger than 5, but less than or equal to 10. Less than or equal to 10. Well, we could use set Miller notation. Here's that same condition, and it's the set of numbers h, we assume to be real numbers, that satisfy the condition that h is between 5, strictly greater than 5, and less than or equal to 10. And interval notation is about a shorter way to write that. We write the left endpoint and the right endpoint, and we put them with brackets, and there are round brackets that look like this. That means that we don't include the number, the endpoint, but square brackets do. So we used a square bracket for 10 because we want 10 to be in that set, and we used a round bracket for 5 because we don't want 5 to be in that set. Here's another example. Okay, here we do want to include 5, but we want to exclude 10. Well, the inequalities just flip, and the set builder notation looks about the same, but now we have a square bracket around 5 and a round bracket around 10. If we don't want to include either 5 or 10, well, it's a strict inequality both ways. And interestingly, this is round bracket 5, 10 round bracket. And this is a little bit problematic because you might confuse this for the point 5, 10 with x coordinate 5, y coordinate 10. Sometimes notation in mathematics is ambiguous. Okay, in this next one, the interval goes all the way to the left, all the way. It keeps on going, and I just write an arrow to show that it goes to negative infinity. And so there's no endpoint there. It goes all the way to infinity, and we'd write that. In set Miller notation, we don't need to write that h is greater than infinity because every real number is greater than infinity. But in interval notation, we do want to write negative infinity. Yeah, negative infinity is on the left. Its infinity is on the right. And of course, we use a round bracket because infinity and infinity are not real numbers. The next one, what if we want the numbers that are starting at 10 and moving all the way to positive infinity? Well, same idea. In set builder notation and the inequality, it's just a single inequality, but 10 is the left endpoint. We do include it with a square bracket, and we do need a right endpoint, so we'll use infinity just to denote that there's no right endpoint, and we'll use a round bracket just because infinity is not a real number. If we want to describe all real numbers, we could just write it in words or use this funny symbol, r, but we're just saying that the number is, there's no lower bound and there's no upper bound, so it's the interval from negative infinity to infinity. One more thing, if we have two intervals that we want to paste together, we'll use set union, and that's that symbol that looks like a U. So let's go ahead and use them. Here are some functions, and we want to describe the domain. And so what we're actually doing is we're looking for the largest subset of the real numbers possible. Okay, and over here, We call this a polynomial. That's a type of function that includes multiplication, addition, and subtraction. And if you input a number, let's input 1, we're going to take 1 and square it, and we're going to subtract what we get when we multiply 7 times 1. So that's 1 minus 7, and that's negative 6. And so that was really fine. There was no problem with that. So 1 is in the domain. So let's see, 1 in domain of f. Well, there's really nothing that's going to go wrong. So we can see that every real number is also in the domain. So we could either write R like this, the real numbers. We could write all real numbers. And in interval notation, we're going from negative infinity to infinity. And those are 3 ways to write the correct answer for the domain of G. Let's look at G, though. Here we're dividing, and when we see that a ratio of polynomials, it's a rational function, rational from ratio, and that means that we're also dividing. Over here in polynomials, there is multiplication, addition, and subtraction. We can build up the function out of that, but for a rational function, we can build it up out of multiplication, division, addition, and subtraction. And the danger is that if you're dividing, you might divide by 0. And remember, that's undefined. Nothing bad happens, but it's just undefined. So we want to avoid dividing by 0. And that happens, so if the denominator x minus 1 is 0, and that happens at x equals 4. So let's look at the number line. The problem is at 4. So we want to exclude 4, and we can use every number to the right of 4 all the way to infinity, every number to the left of 4 all the way to negative infinity. And this left part, the number x can be between negative infinity and 4. We have to use a round bracket at negative infinity, and we want to exclude 4, so we'll use a round bracket there. And this other part, it goes from 4 to infinity, and we want to exclude both of them. 4 because 4 would make the denominator 0. Infinity is not a real number. We want to glue these together, and we'll use that union symbol. So the domain of G is the union of those 2 intervals. Let's do something harder. Here are 2 more functions, and what we have is a square root in both of those, and one is a ratio. And if you see that, you want to avoid the square root of a negative number. Well, mathematically, you can take the square root of a negative number, but you get a complex number or an imaginary number, and we want to avoid that in this class. So let's call this y. Let's do f first. So f of x is the square root of this number y, and we must have y greater than or equal to 0. So let me plot y equals x squared minus 3x minus 40. If I plot that, it's a parabola, and it goes down like this and then goes up, and we want this to be positive. So this is good. Over here, all of these points, the y coordinate is positive, And over here on the left side, they're also positive, that's good, but down in the middle, they're negative. So the actual domain of allowable x-coordinates, the x-coordinates, here's the x-axis, here's the y-axis, the allowable domain are right over here and every x value to the right, and over here, the other x-intercept and every x value to the left. So we just have to figure out where those are, and for that, it's helpful to factor. We want to factor this polynomial, and I actually know the answer. It's going to be x plus 5 times x minus 8. If you're not sure how to do that, that's a good reason to make an appointment with one of our course tutors and ask about factoring quadratics. So this factor corresponds to x equals 5. This factor corresponds to x equals 8. So here's 8 over here. Here's negative 5 here. And that means that the domain includes the interval from negative infinity to negative 5. Let's put a square bracket because that's okay. It's okay for the y value to be 0. And we'll union that with the other interval starting at 8, including 8, all the way to infinity. And so this is the domain. That's the domain of this first function of f. Now, how about g? G has a couple things going on. We want the square roots. We want x minus 7 to be bigger than or equal to 0. And there's another square root. We want x minus 3 to be bigger than or equal to 0. And we're also dividing. So we want x minus 3 to not equal 0. Otherwise, we divide by 0. So we can combine these two considerations to realize that x minus 3 has to be strictly greater than 0. And I'm just going to graph that on a number line. That's convenient. Here's 3 and here's 7. And this first condition, x minus 7 is greater than 0, means that, or equal to 0, 7 is okay, and every number to the right is okay. And the second one, x minus 3 is strictly greater than 0, means not 3, but everything to the right is okay. But we have to, both conditions have to be true, so the domain is up here. Here's the domain of g, and that's going to be x is greater than or equal to 7, and in interval notation, we're going to go from 7 to infinity. And so let me leave it in interval notation. And that's interval notation. There's just a few things to watch out for. Division and square roots, and we'll see some more things to look out for later when we look at logarithms. But that's it for this part of the video.